In this video, I will show you how to find the resultant vector when you have two vectors that are acting together, even when the direction is not simply north, south, east, or west. Now, the key to my process is organization, and I want you to use a chart like this to keep your work straight. And here's how it works. Let's see, an airplane is flying in the direction south, 60 degrees west with an airspeed of 450 miles per hour. It encounters a 65 miles per hour wind in the direction of south, 25 degrees east. What are the resultant speed and direction of the plane? So there are two vectors involved. There's the plane velocity, and there's the wind velocity acting together. So that's what these columns are for. The third column is for the resultant that we're looking for. Now, in the first row, we will record the magnitude and direction of each vector. And in the second row, we will convert to component form. Okay, so the chart will guide you through the process as well as keeping you organized. So start by finding the magnitude and direction for each of the two vectors involved. So a plane is flying in the direction of south 60 degrees west with an airspeed of 450 miles per hour. The 450 miles per hour is the magnitude. Okay, now how about the direction? So let's see, let's do a little diagram for the direction. All right, of course this is north, south, east, and west. South 60 degrees west means start at south and then turn 60 degrees towards the west. So this is 60 degrees, and that's where the vector should be. Okay, so on the chart, however, what we need is the direction as measured from the positive x-axis, measured counterclockwise from east. So for the chart, we need to record this direction. Okay, so how will we do that? It would be helpful if we had the reference angle right here between west and the vector. These are complementary, of course. They add up to 90. So if this is 60, then that means the reference angle right here must be 30 because they have to add up to 90. That means the direction, which we call theta, all right, measured from the positive x-axis, should be 180 plus 30, so that's 210 degrees. And that's what goes on the chart. Let's do the same thing for the wind vector. There's a 65 mile per hour wind, so that's the magnitude right there, 65 miles per hour. The wind direction is south, 25 degrees east. So south, 25 degrees east means start at south and turn 25 degrees towards the east. So this is 25 degrees, and the vector is here. Again, it would be helpful to have this reference angle. So 90 minus 25 will give you the complementary angle. So a reference angle is 65. For the chart, we need the direction measured from the positive x-axis. So we need the direction that goes like this. Okay, and that's going to be 360 minus 65. And that will be our theta. 360 minus 65, that's 295 degrees. So that's the angle that we need for the chart, 295 degrees. All right, so we have now found the magnitude and direction for each of our two vectors. There's no way to directly add these and come up with the resultant. So the first thing we need to do is convert these into component form, x comma y. And here's how you do that. If you want to find the horizontal component, you do r cosine theta, and that will give you the horizontal component. You can get the vertical component by doing the calculation r sine theta. Okay, so looking at the plane velocity, we can find the horizontal component by doing 450 cosine 210. All right, that's r cosine theta. And the vertical component will be 450 sine 210. And we can just use a calculator to evaluate this. Turns out that the horizontal component is negative 389.71, and the vertical component is negative 225. And we just record that on the chart right here. Now we can move on to the wind velocity. And so again, we can find the horizontal component by doing r cosine theta. So that's 65 cosine 295. Vertical component is r sine theta, so 65 sine 295. And we'll just use a calculator to evaluate this. So the horizontal component is 27.47 and the vertical component is negative 58.91. And we'll just record that on the chart here. Now, in component form, you can find the resultant by simply adding these two vectors together. So we will add the corresponding components. All right, horizontal plus horizontal and vertical plus vertical, and we'll simply record the resultant here. So the resultant vector turns out to be negative 362.24, comma, negative 283.91. So that is the resultant vector in component form, but we need to rewrite it as a magnitude and direction. So let's start with the magnitude. For the magnitude, we can just use the magnitude formula and do negative 362.24 squared plus negative 283.91 squared, and take the square root of all that with a calculator. So the magnitude is 460.24. Now, let's put that back in context. So we're saying that the speed of the plane is 460.24 miles per hour with the effect of the wind. Now, we also need the direction of the plane with the wind. We need the direction of this resultant vector. So let's figure that out. Okay, let's make a little diagram. So we have negative horizontal component and a negative vertical component. That means, let's see, north, south, east, west. That means we are west and south, or left and down on this graph. That puts us in the third quadrant. So let's draw a vector into the third quadrant. Now let's consider the vertical and horizontal components here. So we have the vertical component and the horizontal component. So the horizontal component goes here, negative 362.24. The vertical component goes here, negative 283.91. Okay, now we can find this reference angle by using tangent. Because the tangent of the reference angle should be 283.91 over 362.24. You really can ignore the negative signs when you're doing the reference angle, because we just want the positive size of the reference angle anyway. So if you want the measure of the reference angle, you will do the inverse tangent of this fraction. In your calculator. So this reference angle is 38.09 degrees. Okay, now what we often do is we will now measure the direction from the positive x-axis. So if I were to do that, it would look like this. And we call this theta when we measure from the positive x-axis. And we would calculate theta by doing 180 degrees, which is what we have at west. But then we're going an additional 38.09 degrees. So if we did that, we'd get a direction of 218.09 degrees. All right, 218.09 degrees. So now we have the magnitude and the direction. However, in this particular case, we cannot leave this as our final answer. The reason why is the direction. We converted to a method of giving direction measuring from the positive x-axis. However, in the original problem, they gave us directions using this form: south 60 degrees west, south 25 degrees east. So for our final answer, we need to write the direction using that format. So I'm just going to recopy my answer, including my magnitude. So I will say 460.24 miles per hour. All right, that's the speed of the plane. But now I'm going to go back and look at the direction again and give it in a similar format to what was presented in the problem. And you simply must do that. Okay, so since this is in the third quadrant, I am going to measure from south. So what I could say is, starting at south, well, you know what? I'm going to need the measure of this angle right here. Let's figure out how big this angle is by subtracting from 90. This angle is 51.91 degrees. So to arrive at this position, we could start at south and then turn 51.91 degrees in the direction of west. So another way of describing this direction is to say south 51.9 degrees west. Again, meaning start at south, turn 51.9 degrees towards the west. So this is what we will write for our final answer direction. So this is the final answer. Let's do one more problem. And again, let's stay organized by using a chart like this one. A scuba diver swims 100 feet per minute at a direction of east 25 degrees south. The water is moving with a current of 30 feet per minute at a direction of west 10 degrees south. Find the driver's resultant speed and bearing. How far will the scuba diver swim in 15 minutes? So we have two vectors to consider. We have the velocity of the swimmer, and then we have the velocity of the current. Acting together, we need to find the resultant vector. In the first row, we will record the magnitude and direction of each vector. And in the second row, we will convert to component form, x comma y. So let's see, a scuba diver swims at 100 feet per minute. That's the magnitude of the swimmer's velocity. So 100, and I'm just going to put FPM for feet per minute, at a direction of east 25 degrees south. Okay, let's explore that a tiny bit. Okay, east 25 degrees south. That means start at east and turn 25 degrees towards the south. So start at east and turn 25 degrees towards the south. So this is 25 degrees right here, and the vector is here. Now, on the chart, we have to measure from the positive x-axis. So the angle that we need for the chart is going to be the angle that I'm showing now. Okay, we call that theta, and we can get theta in this case by doing 360 minus this 25 degree reference angle. Okay, and so that's going to be 335 degrees, and that's what we record on the chart. Now, the current is moving at 30 feet per minute. That's the magnitude. At a direction of west 10 degrees south. Okay, so that means start at west and turn 10 degrees towards the south. So this vector is here. Okay, but for the chart, we need the angle that would be measured like this. All right, so we will call that theta, which in this case we could get by doing 180 plus the extra 10 degrees. So that's going to be 190 degrees, and that's what we record on the chart. Okay, for the chart, you always need the angle measured from the positive x-axis. Now, there's no way to directly add these and come up with the resultant that we need, so we're going to have to convert them into component form, x and y. Now, if you know the magnitude r and the direction theta, measured from the positive x-axis, you can find the horizontal component by doing r cosine theta, and you can find the vertical component by doing r sine theta. So for the velocity of the swimmer, the horizontal component will be 100 cosine 335, and the vertical component will be 100 sine 335. And we can use a calculator to evaluate this. The horizontal component is 90.63, and the vertical component is negative 42.26. So we record that on the chart like this. Similarly, for the current, we can convert this magnitude and direction into component form by doing 30 cosine 190 and 30 sine 190. And again, calculator. The horizontal component is negative 29.54, and the vertical component is negative 5.21. And we record that right here. Now that we have component form, we can find the resultant vector by simply adding these two vectors together. Add corresponding components, horizontal plus horizontal, and vertical plus vertical, and then just record that here for the resultant vector. So the resultant vector in component form is 61.09 and negative 47.47. So now we need to find the magnitude and direction of the resultant, which we will put right here. Okay, so let's start with the magnitude. Which we can simply find using the magnitude formula. So we will do 61.09 squared plus negative 47.47 squared, and take the square root of all that with a calculator. So the magnitude is 77.37, and in context, 77.37 feet per minute. All right, that is the speed of the swimmer once you take into account the effect of the current. Now, we need the direction of the swimmer with the current, the resultant direction. So let's find that. So direction. But let's start with a diagram. The horizontal component is positive. The vertical component is negative. That means we are going to be east, west. That means we are going to go to the right and down on this graph. So that puts us in the fourth quadrant. So go ahead and draw a vector in the fourth quadrant. And now let's imagine the horizontal and vertical components of this, which would be something like this. Okay, the horizontal component is 61.09, and the vertical component is negative 47.47. Now, it will be useful to know the reference angle right here. So the way we can find the reference angle is by using tangent. So the tangent of this reference angle should be 47.47 over 61.09. Notice I'm ignoring the negative sign because I really just want the positive value of this reference angle. To find the reference angle, I will do the inverse tangent of the fraction, 47.47 over 61.09. Just use a calculator. Now, oftentimes what we will do is measure the direction from the positive x-axis like this. All right, we would call this theta, and we could find theta in this case by doing 360 minus the reference angle 37.85. That's 322.15 degrees. And then we would record that on the table. So 322.15 degrees. But we must be careful with direction because there are 4 different methods that are used to report the direction of a vector. And in our final answer, we need to be careful to use the same type of direction that they gave in the original problem. So here I see directions like east 25 degrees south, that type of thing. So I'm going to look again and come back with that type of direction. So I'm just going to rewrite the whole thing, the magnitude and the direction. So the magnitude is not going to change. So we have 77.37 feet per minute. But now let's go back and take another look at the direction. So I can use this reference angle to have another name for the direction. We could think of it as starting at east and then moving 37.85 degrees in the direction of south. So this would be another form of stating the direction, but one that matches the way they gave direction in the original problem. So this is what I'm going to record. So this is how you would write your final answer, or one of the final answers. So I seem to recall they asked an extra question at the end of the problem. So let's look back and see, and let's remember what the extra little question they asked at the end was. So we found the resultant speed and direction. That's great. But then they also asked, how far will the scuba diver swim in 15 minutes? Okay, so look, you have to remember that distance equals rate times time. Distance equals rate times time. Okay, so we want to find the distance that he swam. So all we need is the speed and the amount of time. So obviously the amount of time is 15 minutes. So that means all we need is the speed. Okay, and the resultant speed of the swimmer, once you take into account the current, was 77.37 feet per minute. All right, so 77.37 feet per minute times 15 minutes. That should give us the distance. So that's 1,160.55 feet. All right, so that's the answer to the extra little question.